Hello, I'm going to introduce you to emergence. This is the alternative topic to the logic unit that Stanford introduces here. While logic is useful for some practical implementations of AI, I think emergence is an exciting field and will be a very important field in the future of AI. So I wanted to introduce that to you. A good place to start is this Nova Science Now video. You can click on that, download the video, or watch it streaming. It's a great short introduction to emergence. And also one of my favorite podcasts of all times is on emergence from Radiolab. I don't know if you're familiar with Radiolab's podcast, but this is a podcast you go here, listen to it here, or download it to your favorite smartphone or MP3 player. I've enjoyed it so much, in fact, I've forced both of my children who are college age to listen to it, even though they're not in this class. There's also links to the Wikipedia article, and this is a nice contrast between entropy and emergence or self-organization. One of the classic examples when you're first looking at emergence is flocking behavior. Emergence is where we have simple rules that generate complex behaviors. So let me just open up this flocking behavior and talk a little bit about this. So for a long time, people did not understand how birds, fish, insects flocked or what caused their behavior in different ways. And till we got to computers and were able to run some simulations, people wrote a simple set of rules for flocking. Each object had a zone where it'd like to be. You can actually set that zone here. And if another object was outside that zone, if there are no other objects, birds within their zone, they just found the nearest bird and flew towards that. If there was a bird too close to them within that zone, they would just fly away from that other bird or other object, other fish. And if there were objects within that zone, which we kind of call the Goldilocks zone, not too far, not too near, they would just fly in the same direction as the other object and align themselves. So with those three simple rules, which are easy to program in, you can write these simulations and generate rather complex behaviors. And here you can actually change some of these zones, and this flocking behavior, the birds or whatever the objects are, they follow the mouse somewhat, but they don't have to do that. So there's a couple other versions here. This is one that they fly around kind of in 3D, they fly away and back and stuff, but they also have these wires they tend to land on and stuff. So you can watch that for a little bit. You can't interact with that one. And then there's the original one called Floyd's. You have to run this Java application and maybe make it a little bigger for you. And I can change the number of Floyds I have here and run this and maybe slow it down. So again, you can run these simulations and watch how they work and the complex interactions that are generated by these simple set of rules. And so again, that's one of the keys to emergent behaviors. We have many objects governed by simple rules. We have some interactions between these objects over time, and the rules are applied to each other again and again. So the rules are repetitively applied, and rules don't restrict the outcomes. They're set up some way so that they're real general rules. If the rules are set up correctly, you generate some really complex, interesting behaviors. A good example is Conway's Life. It's a simulation game that kind of simulates bacteria or something like that. You'll have to see it. There's a good introduction here, but I'm going to show you a couple simulations of it. So again, I can draw dots, and the idea of life is some dots are alive and some aren't. And then I can run this, and they evolve. The dots will change over time and generate some really interesting behaviors. But the rules are relatively simple for these. There are some really simple rules that you can generate for this. So I want you to look at the rules for life. Things like for every cell, we look at the neighbor cells. And if of the 8 neighbors, if there are not very many neighbors around that are alive, a cell dies of loneliness. If there are too many neighbors around, a cell dies of overcrowding. And sometimes if there's just the right number of neighbors, a cell will be created, life will be created for the simulation. So you can run these simulations and explore them. But it's amazing what complex behavior is generated by these simple behaviors. So you can look through that and learn the rules for that. Now this is part of a more general area called cellular automata, and there's some links to some more general examples of cellular automata. Okay, so we've looked at flocking behaviors, Conway's life simulation. Another area is what's called chaos theory or chaotic systems. There are some great books and stuff written about chaos theory, and so this is a good link to that. Chaotic behavior is behavior that almost seems random but isn't. And there are slight changes in the initial characteristics can generate profound changes over time. So an example they haven't talked about is the weather is often chaotic. Small changes in our parameters affect changes over time, and these changes, these effects build over time. That's why, although it's with our weather modeling, it's okay. We can enter the current parameters and predict what the weather is going to be like relatively well tomorrow, maybe the next day. But each day, the weather is dependent on the day before's prediction, and these predictions build on each other. And so after 5 days or so, it's really hard. Slight changes in our current conditions have drastic effects over time and the long-range predictions. We're going to look at a really simplified version of this called the logistics function. So let's look at the logistics function. This is the Wikipedia entry on it. It's a function where we take number x and multiply it by 1 minus itself. And so we want x to be between 0 and 1 generally. And then we generate a new x, and we take that new x and plug it into the same equation to generate another x. And there's this parameter r that we change at times to get different behaviors. So we'll always be plugging in our number, getting a new number, and plugging that into our equation again and getting a new number, plugging it x in here, and getting a new x here or y. So here I show you what if the r value is 1, then our function is just x times 1 minus x is y, and then we set y equal to x and redo it. We could make r2, r3.5, 3.6, and as we change the r value, the behavior of this function changes dramatically. Here's where here the parameter r they labeled a in this simple simulation. This you can get at using this applet. And so I can try with a different parameter here. You have 2.0, and what's interesting is at 2, all the numbers, all my initial conditions that I start, if I start at 0.1, it'll end up going to the same number. If I start with another number, it'll end up going to the same number. Now if I increase this to like 3.5, and draw this, I get some different behaviors in that the values of my of this function change over time. They change. They just don't go to one fixed value and stay there. This actually oscillates through a number of different values. So by changing this parameter here, I can get very different behaviors. Wikipedia has a nice routine here that shows as we change this parameter, it's going up to 3.2. I'm now oscillating between 2 values here, and now I'm getting some really strange behavior, and then things just go crazy. And that's what chaos is where things are just going crazy almost here, and then it stops for a bit, but it gets really weird. It seems random, but it's not. So that's the logistics function. You can play with that a little bit. Finally, we'll look at fractals. Fractals are complex graphical objects where we take a point and we have some equation for reiterating the point. A simple fractal is this fractal fern where there's simple rules for generating this sort of a fractal where the same object is repeated and repeated and repeated again. So we take a simple object and repeat it over and over again, each time doing slight rotation. So this little part of the fern is simply this large fern rotated and moved over here. So see, this fern looks just like the big fern, and then this little leaf looks the same. And so by doing this repeating and stuff over and over again, we can generate some very complex behaviors. But we're going to look more at this Mandelbrot set and look at this view of it. And what's interesting about the Mandelbrot set is you can zoom in on different parts of it, and you can see amazingly complex behaviors of it. But the set itself is rather simple. This is x and y coordinates, and this is 0 on the xy coordinates. And you pick any point in here and you apply a set of equations, relatively simple equations, to this point, the x and y coordinates. And you get a new x and y coordinate, and you apply the same set of equations, you get a new x and y coordinate. A lot of these coordinates will go to 0 over time. You update them, apply these two equations to the x and y values, and you end up at 0. So all the values in black go down to 0. All the numbers not in black get slowly larger as you update the equations over and over again. You'd think just updating equations, you just end up with some simple circle or whatever, but you end up with an amazingly complex boundary of these systems. That you have. So we'll walk you through some examples of this and show you what the equations are. So there are 4 activities. One is working with emergence and artificial life and trying to make sure you understand the rules and then try out some of the simulations. The other one is with chaos theory, using the logistics function, calculating these values again and again with like a spreadsheet or just a calculator you can use. So we start with some initial value, we calculate a new x value, we use that, plug that in to calculate another x value, and repeat that and see what it imagines, what it procures. And then we look at fractals, the Mandelbrot set, and again, these are the simple rules for calculating the Mandelbrot set. If given an initial x and y coordinate, we are just, in this case, we're just taking the x coordinate, squaring it, subtracting the y coordinate squared, and adding the x coordinate back in. And we apply that again and again, and we get this really strange behavior. And finally, the final activity has to do with flocking and running one of these simulators and seeing what you can find out about them. So those are the 4 activities. Again, you can choose between the logic activities and the emergence activities this week.